In this lesson, we're going to review some trigonometry concepts that we'll use throughout this course. Now in this course, we're normally going to be using radian measure for angles as opposed to degree measure for angles. Now sometimes we will use degrees in problems, so you should know how to change your calculator setting from radians to degrees and degrees to radians. And also, all of our trig functions are defined with respect to radian measure for angles. So let's review exactly what a radian is. Now down here, we have the graph of the unit circle. We call it the unit circle because it has a radius of 1. Notice the distance from the center to the outer edge is 1. So we call this our unit circle. And we have labeled here an angle theta measured counterclockwise from the positive x-axis up to the line segment determining its terminal side. And we have theta listed as equaling s radians in this picture. Now that s is some number that would be given to us. So what does that s actually represent? Well, that s actually represents the distance along the outer edge of the unit circle. From this point, which is 1, 0 on the x-axis, up to the line segment determining the terminal side of the angle. So this s actually represents a distance along the outer edge of the unit circle. That's what radian measure represents. For example, this angle right here looks like it might be about a 45-degree angle. Now 45 degrees, as we'll review, is equal to pi over 4 radians. And if you evaluate pi over 4 on your calculator, you'll get 0.785 approximately. And that 0.785 actually represents the distance along the outer edge of the unit circle, as we have labeled here. Now if your angle is measured in a clockwise manner like this, so if our angle theta were measured like that, well then theta would be a negative number, but the absolute value of that negative number would still represent the distance along the outer edge of the unit circle. For example, in this picture right here, it looks like theta would equal, well, negative 45 degrees again, which is negative pi over 4 radians. And of course that is negative 0.785 approximately. And so if we take the absolute value of this, that'll give us back positive 0.785. And so that is the distance along the outer edge of the unit circle between these 2 points, from here to here. So if theta is measured in a clockwise manner, then it's represented by a negative number. Now let's review some common angles that we'll be using throughout this course. Now let's recall that the area of a circle of radius r is pi r squared. We need to know that. And the circumference of a circle, the distance along the outer edge, is pi times diameter. And since the diameter is twice the radius, we can say that's also 2 pi times r, since the diameter is twice the radius. So for the unit circle, the distance all the way around the outer edge of the unit circle is going to be 2 pi, because the radius is equal to 1 for a unit circle. Now down here we have a graphic illustrating the correspondence between degree and radian measure for some common angles. For example, 30 degrees, which would be this angle right here, corresponds to pi over 6. 45 degrees corresponds to pi over 4, 60 degrees is pi over 3, and so on. 90 degrees is pi over 2, 180 degrees is pi, 270 degrees is 3/2 pi, and 360 degrees is 2 pi. Notice that 360 means that you go all the way around, like that, and if you go all the way around the outer edge of the unit circle, well, that distance is 2 pi. So 360 degrees corresponds to a radian measure of 2 pi, and that 2 pi actually represents the distance along the outer edge of the unit circle. Now also notice, let's pick an angle here like 45 degrees. Why is 45 degrees equal to pi over 4 radians? Well, 45 degrees we see is 1/8 of 360 degrees. You can see that if you just put a line segment in here. Okay, so this angle right here looks like it's 1/8 of 360 degrees, and that's exactly what it is. So if we go all the way around the outer edge of the unit circle, well, that distance would be 2 pi. And if we divide that by 8, that will give us this distance along the outer edge of the unit circle, right there. And that distance is going to be 2 pi divided by 8, and that's pi over 4. So that's why 45 degrees corresponds to pi over 4 radians. Now let's review the conversion equations between radian and degree measure. So recall that to convert degrees to radians, you multiply the degrees by pi over 180. And to convert from radians to degrees, you multiply the radian angle by 180 over pi. So for example, let's convert 30 degrees to radians. We saw on the diagram that we just saw that 30 degrees corresponds to pi over 6 radians. So we can get that immediately from these conversion equations. So to convert 30 degrees to radians, we simply multiply 30 times pi over 180, and 30 over 180 is going to be 1/6, right? You can see that, just cancel those zeros out. 3 over 18 is 1/6, and so this becomes pi over 6 radians. So 30 degrees is equal to pi over 6 radians. Let's convert 5 pi over 6 radians to degrees. So in this case, we'll need to multiply by 180 over pi. So 5 pi over 6. So to convert that to degrees, we'll multiply it by 180 over pi. Now we just have to simplify this. 5 pi over 6 times 180, well, we see let's note that the pi's cancel here first. 6 over 180 is going to be 30, right? 18 over 6 is 3. So 180 over 6 is 30, and so this is going to be 5 times 30 degrees, or 150 degrees. So 5 pi over 6 corresponds to 150 degrees. And we can see both of these if we go back to that graphic we saw earlier. Right here we see 30 degrees corresponds to pi over 6, and 150 degrees corresponds to 5 pi over 6 radians. Now let's consider arc length. If you're given a circle of radius r, so that's your radius of this particular circle right here, and suppose you want to know the distance along the outer edge of the unit circle? Well, if r is equal to 1, then the distance along the outer edge would just be the angle in radian measure. That's exactly what radian measure gives us. But if r is not equal to 1, then to find this arc length, you simply take theta and multiply it by r. That's all you have to do. So for example, suppose the second hand on a clock is 5 inches long. Let's find the distance the tip of the second hand moves as it goes from 1 to 3. So I paused the video for a second and drew a diagram down here to help us. So for this problem, here we have a second hand right here, and it moves from the 1 position down to the 3 position right here, and we want to find this distance along the outer edge of that circle. Now the second hand is of length 5, so that's going to be the radius of this circle, and so we need to find that distance. Well, from our formula up here, we simply have to multiply the radius, which is 5 in this case, times the angle theta. And we have to find out what is this angle theta right here. Well, notice that this is a 90-degree angle right here. Right here we have a 90-degree angle, and it looks like theta is going to be 2/3 of 90 degrees. So the angle theta is going to be 2/3 times pi over 2, or just pi over 3, which is 60 degrees. And that makes sense from this picture that that should be 60 degrees. So then the length, or the distance that the tip of the second hand moves as it goes from 1 to 3, this distance that we're trying to find right here, s, the distance from here to here, that's simply going to be r times theta, which is going to be 5 times pi over 3. And if you want to get an approximate answer, you can use a calculator to get 5.24 inches. So that's how far the second hand travels, the tip of the second hand travels, as the second hand moves from the 1 to 3 position on the clock face. For our second example here, a similar problem, but we want to find an area. So the second hand on a clock, still 5 inches long, find the area swept out by the second hand as it moves from the 1 to 6 position on the clock face. So down here, I paused the video and drew a picture of what we need to find. So here we have the second hand, and it is traveling from the 1 position to the 6 position. The radius, or the length of the second hand, is 5, and we want to find this area. So the area in here, as the second hand sweeps from here to here. Now let's notice that that green angle right there, theta, well, what is that angle going to be? Well, the entire angle here, if we go from the 12 o'clock position to the 6 o'clock position, that's going to be pi, and this little piece right here is 30 degrees, or pi over 6. So this angle right here, theta, is going to be pi minus pi over 6, or 5 pi over 6. So that's what that angle theta is. Now let's recall the area of a circle. The area of a circle is pi r squared, pi times the radius squared. So if we were to continue all the way around, the area of the entire circle of radius 5 would be pi times 5 squared, or 25 pi in this case. Now this sector right here is not the entire circle, of course, so we have to figure out what is the fractional part that this sector is of the entire unit circle. Well, notice that if we were to go all the way around, we would sweep out an angle of 2 pi. So to get the fractional part that this sector is of the entire circle of radius 5, we can just evaluate 5/6 pi divided by 2 pi. The pi's will cancel here, and we get 5/12 pi. Oh, just 5/12, sorry. And once again, you can get that by multiplying top and bottom by 1/2 to cancel out that 2. So that's how you get 5/12. So then the area of the sector swept out by the second hand is going to be 5/12 of this entire area. That's the area of the entire circle of radius 5. So our answer is going to be 5/12 times 25 pi, and that is approximately 32.725. And the units there would be in square inches. Now let's review the definition of the 6 trigonometric functions that we'll be using throughout the course. So first of all, remember that to define the 6 trig functions, there's 2 ways we can do it. One way is to use the right triangle approach, where we have a right triangle drawn here. So this angle down here is a 90-degree angle, or pi over 2 radians. And we label the length of the opposite side. This side is called the opposite side because it's opposite our angle theta down here. We label this side as our adjacent side because it's adjacent to theta, and this side opposite the 90-degree angle is called our hypotenuse. So we have our opposite, adjacent, and hypotenuse lengths for this triangle. Those would be given to you. Now the definition of our 6 trig functions are as follows then. The sine is the opposite side over the hypotenuse. So the length of the opposite side divided by hypotenuse. That's what we define to be the sine of theta. Cosine theta is adjacent over hypotenuse. Tangent is opposite over adjacent. And then we have our other trig functions. The cosecant is 1 over the sine, and since sine is opposite over hypotenuse, the cosecant is going to be hypotenuse over opposite. The secant is 1 over cosine, or hypotenuse over adjacent, and the cotangent is 1 over the tangent, or adjacent over opposite. Now, sometimes it's a little more useful to define these trig functions using the unit circle definition, and that we have defined below. So here we have drawn a unit circle, and we have labeled this point right here as x comma y. So x is our adjacent side now, so this is the adjacent. Y is the opposite side, that's the length of the opposite side, and notice our hypotenuse is always 1 now. So then we can just define the sine of theta to be opposite over hypotenuse, or just the coordinate y. That's all it is. It's just this coordinate right here. That's going to be the sine of theta. The cosine of theta is adjacent over hypotenuse. Well, in this case, that's just going to be x over 1, or just x. Tangent, opposite over adjacent, so y over x. And then we have our other corresponding trig functions. Cosecant is 1 over y. because cosecant is 1 over sine. Secant is 1 over x, because secant is defined to be 1 over the cosine function. And cotangent is x over y, since cotangent is 1 over tangent. So these are the unit circle definitions for the trig functions. Now let's take a look at this example. Here we are given a right triangle, meaning that this angle right here is 90 degrees. And we want to find the angle alpha and the length of the side x. Now keep in mind here we are dealing with degree measure. So to find the angle alpha, recall that if you sum all the angles in a triangle, those angles must sum to 180 degrees or pi radians. Remember, 180 degrees and pi radians, they're the same thing. So for this picture that we have here, 36 degrees plus 90 degrees, which is this angle right here, plus alpha must equal 180 degrees. And solving that, we get that alpha is 54 degrees. So we know that this angle right here is 54 degrees. Now to find the length of the side x, recall that the tangent is opposite over adjacent. Now in this case, 12 is going to be our opposite side if we're using the angle 36 here, and x is going to be the adjacent side. So the tangent of 36 degrees is 12 over x, and solving that for x, we get that x is 12 divided by the tangent of 36, and that's approximately 16.5166. So that's the length of the side x. Now keep in mind when you're evaluating this on your calculator, make sure that your calculator is in degree mode. You could also convert 36 degrees into radians if you wanted to, and then use radian mode on your calculator. And 36 degrees is 36 times pi over 180 radians, and 36 divided by 180 is 1/5, so this is actually pi over 5 radians. So you could evaluate x as 12 divided by the tangent of pi over 5 radians, and you'll still get 16.5166. Now, we're not asked to find this in our problem, but if we wanted to find the length of the hypotenuse h, we could also use the trigonometric functions. Recall that the sine is opposite over hypotenuse, so we could say that the sine of 36 degrees is 12 over h. And then solving this for h, we get h is 12 over the sine of 36 degrees. And then you can just evaluate this on your calculator. Now we could also use the Pythagorean theorem here, noting that by the Pythagorean theorem, h squared is equal to 12 squared plus x squared. So h is the square root of 12 squared plus x squared. And you could put 16.5166 in for x and evaluate h. However, it's better to do it like this, because if you put this into your calculator, it will give you much less round-off error than if you were to plug in 16.5166 in here for x. Now, if you took out more decimal places here in your approximation for x, then you would get a reasonably good approximation up here for h. But it's a little easier just to use this trig definition over here if you're using your calculator. Now let's consider the graphs of these trig functions. It's very important throughout this course to understand what the graphs of the sine, cosine, and tangent in particular look like. So here we have the graph of the sine function. Now to understand, right here is the graph of the sine. This is it right here. Now to understand where that graph comes from, consider the diagram on the left over here. Here we have an angle theta drawn. Right now, let me move that slider just a little bit. So right here we have an angle theta drawn. Notice that we have our x and y coordinates listed here. And so for this particular diagram, the sine of theta, in this case theta is 0.73, that's the distance from here to here. The sine of theta is the y coordinate, remember y over 1 from our previous definitions. That's going to be 0.67. So therefore this point, 0.73, 0.67, right there it is, that would be a point on the graph of the sine function. So as we let this angle sweep around, what we do is we plot out the points theta, comma, and then whatever our y coordinate happens to be. So this point will get plotted over here, and that will give us the graph of our sine function. So let's see what happens as we do that. So notice that we start when theta is the angle 0. Now it's a little difficult to see there, but when theta equals 0, notice that the y coordinate of that point right there is also 0. So we plot the point 0, 0 right there on the graph of the sine function. And then as we let this angle increase, watch what happens. Watch the black dot over here. This black dot will be plotting out the points theta, comma, y, and we will get the graph of our sine function. Notice at this point right here, our sine function has a maximum value of 1, and that's when theta is pi over 2. So this point right here on the y-axis here, on the theta axis, would be pi over 2. And as we continue around, notice at this point right here, our angle theta is pi. The y coordinate of this point right here is 0. So we plot out the point pi, comma, 0 on the sine function, and right there it is. And then we just continue. And notice how we're tracing out the graph of the sine function. And backwards also. These are all negative angles back here. Okay, so right there is the angle negative 0.82 radians. Now the important thing to note here about the sine function is that it starts at 0, 0. It has an amplitude of 1. And it has a period of 2 pi. That's how long it takes to repeat. So notice that after 2 pi units on the theta axis here, which corresponds to the x-axis, the sine function just repeats again. So this is our main branch right here of our sine function, right there. And then everything else is just a repetition of that piece of the sine function. For the cosine function, it's very similar, except when we have this point right here, when we're given this point right here, on the graph of the cosine curve, we're going to be plotting the point theta, comma, the x coordinate of this point up here. Because remember, the cosine of theta is adjacent over hypotenuse, and this is the unit circle here, so our hypotenuse is always 1, and the adjacent side is our x-coordinate in this case. That corresponds to the adjacent side of a triangle drawn like this. You see that's x right there, so this distance is x. And so as we let this angle continue, we will plot out these points right over here on the graph of our cosine function. And so notice if we start at theta equaling 0, this point right here has an x-coordinate of 1, so we plot the point 0, 1, and then we just continue. And we see we trace out the graph of the cosine function like this. It looks very similar to the sine function, except that instead of starting at 0, 0 and repeating every 2 pi units, it starts at 0, 1 right here, and then goes down and up. It also has an amplitude of 1, that's its maximum height, and it also has a period of 2 pi. After 2 pi units, it starts repeating again. Now here's the graph of our tangent function. Tangent is a little different. So considering this diagram on the left here, if we have an angle theta, and this is the point right here, remember the tangent of theta is defined to be the y-coordinate divided by the x-coordinate of this point right here. And remember the y is the same as the opposite side, x is the adjacent side. So now let's see what happens to this point, which is, for this particular angle right here, representing y over x. Let's see what happens to this point as we let this angle go around the unit circle. So you notice that when we start with theta equaling 0, the y-coordinate is 0, and the x-coordinate is 1. So we're starting at, when theta is 0, y over x is 0. So we start at 0, 0, and then we let the angle continue like this. Now at this point right here, notice that our dot is moving up towards infinity right here. So we went like this. We're going up towards positive infinity as our angle theta approaches pi over 2. And that's because at this point right here, the y-coordinate is getting very close to the number 1, and the x-coordinate is getting very close to 0. When you take a number like 1 divided by 0, a number very close to 1 divided by a number very close to 0, evaluate this on your calculator. For example, try 0.999 divided by 0.0001, and you'll see that you get a very large number. So for that reason, this black dot will be traveling towards infinity as the angle theta is getting closer to pi over 2. So you see the tangent function has a problem existing at pi over 2 right here on the theta axis. Similarly, as we let theta approach negative pi over 2, notice that as theta approaches negative pi over 2, our black dot over here is going towards negative infinity. Because if we evaluate y over x, we're evaluating a number like that's very close to negative 1 over a very small number. Negative 1 over a very small number like negative 0.999 divided by 0.0001 is going to be a very large negative number. So we see that the tangent function has what we call vertical asymptotes here at negative pi over 2 and here at positive pi over 2, and its graph looks like this. And you'll notice it repeats every pi units. So if you take this branch of the tangent function from negative pi over 2 to pi over 2, it looks exactly the same from pi over 2 to 3/2 pi, and so on. So that's what the graph of our tangent function looks like. The graph of cotangent is very similar to the graph of tangent, except we have problems with it existing when theta is 0 and pi. So right here we have the graph of our cotangent function. Remember, cotangent x over y. So you see the cotangent function will have problems existing whenever the y, the denominator here, is equal to 0. And that corresponds to when theta is 0 and pi and multiples of those angles. So for example, here you'll have a vertical asymptote at 0, pi, 2 pi, negative pi, negative 2 pi, and so on. And the graph of cotangent looks very much like the graph of tangent, except it's flipped and shifted a little bit. Now the graph of our secant and cosecant functions look like this. So if we want to sketch the graph of our cosecant function, remember cosecant is defined to be 1 over the sine function. So here's a very easy way to see what the graph of the cosecant will look like. First of all, sketch the graph of the sine function. Now that is the red dotted graph right here. Now notice that since the cosecant is 1 over sine, the cosecant will have vertical asymptotes wherever the sine function is equal to 0, which would be here, 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 and so on. So at multiples of pi. So at these points, that's where the cosecant is going to have vertical asymptotes. And when the sine is equal to 1 and negative 1, like here and here, the cosecant function is going to be 1 and negative 1 as well. Because if I put 1 in here for sine, 1 over 1 is 1. Or if I put negative 1 in for sine, 1 over negative 1 is negative 1. So these points right here will be on the graph of your cosecant function as well. And then notice that as the graph of the sine function, as it goes towards 0, the cosecant function is going to go towards positive infinity. And as the sine function dips down, as theta goes to pi, the sine function will dip down to 0, so the cosecant function will break up like this. So here we have one piece of our cosecant function. It corresponds to this piece of our sine graph right here. And then we have another piece of our sine graph right over here, dips down like that and comes up. And that creates this piece of our cosecant function. And similarly, for other parts of the cosecant curve, over here between 0 and negative pi, and over here between negative pi and 2 pi. Now the graph of the secant function, well, we can do the same thing as we did here to reason what the graph of the secant function will be, but we use the base graph of the cosine curve. So here we have the red dotted line representing our cosine curve. And so we want to graph the secant function, which is 1 over cosine. Well, notice that the secant function will then have a problem existing wherever the cosine is 0, which is at negative pi over 2, positive pi over 2, 3/2 pi, 5/2 pi, and so on. That would be negative 3/2 pi right here, negative 5/2 pi, and so on. And so we will have vertical asymptotes for the secant function wherever these red dots are. That's where cosine is equal to 0. And notice that for this piece of the cosine function right here, the secant graph will break up towards positive infinity like this, and up towards positive infinity like this, as we approach pi over 2 and negative pi over 2, because as we approach those two numbers, the cosine function is approaching 0. And 1 divided by a very, very small positive number is going to be a very large positive number. Once again, try entering something like 0.999 divided by 0.0001, and you'll get a very, very large positive number. So that's why the secant function breaks up towards positive infinity like this. On the other hand, over here, where the cosine function is negative, like from pi over 2 to 3/2 pi, the secant function will be negative because you're looking at 1 divided by a negative number now, and that will be negative. So the secant function looks like this. And so on for other parts of the secant function. We're now going to do a quick review of evaluating trig functions for some of our common angles. So down here we have a unit circle diagram with our most common angles labeled on it, like pi over 6, pi over 4, pi over 3, and so on. Now notice that we have the points on the unit circle corresponding to those values labeled here. And remember that the sine of our angle theta is opposite over hypotenuse, which for the unit circle corresponds to equaling y over 1, where y is the y coordinate of each of these points. Cosine of theta is x over 1, or just x, and our sine was just y. And the tangent of theta is y over x, and this corresponds to opposite over adjacent. Now if you look at our angles over here, to try to remember these points, it's easiest to note this pattern. Note the pattern 0, 1/2, root 2 over 2, root 3 over 2, 1. So you see this is really like, it's pretty easy to remember, it's really like root 1 over 2, root 2 over 2, root 3 over 2. See the pattern? 1, 2, 3. And they're square roots in the numerator. And then in the denominator you just have 2, 2, 2. So you notice those appear as the y coordinates here, here, and here as we move from 0 to pi over 2. And notice how we go from pi over 2 back to 0, how the x coordinates do the same thing, 1/2 root 2 over 2, root 3 over 2, like that. So it's easy to remember these numbers if you remember this pattern down here. And remember that as you go from 0 to pi over 2, the pattern begins with the y coordinate. The 1/2 starts in the y coordinate. 1/2 root 2 over 2, root 3 over 2. And then the x coordinates are their corresponding partners. You can think of it like that. Now let's take a look at this example down here. So let's use this graphic that we have above to evaluate the sine, cosine, and tangent of 5/6 pi. Well, we see right here is 5/6 pi on our graphic, and so the sine of 5 pi over 6, we can just read that right off from the unit circle. That is going to be the y coordinate, which in this case is going to be 1/2. The cosine of 5 pi over 6, that's going to be the x coordinate, which in this case is negative root 3 over 2. And the tangent of 5 pi over 6 is going to be the y coordinate divided by the x coordinate. So that's going to be, and the 2's here cancel, and we get negative 1 over root 3. And if you want to remove the radical from the denominator, you could multiply top and bottom by the square root of 3 to get negative root 3 over 3 if you want to rationalize that denominator. Now suppose you didn't have this unit circle diagram in front of you and you still wanted to evaluate sine, cosine, tangent of 5 pi over 6. How can you remember what those values are? Well, as long as you remember what's going on in the first quadrant here, you can deduce what's going to happen in the other quadrants. For example, suppose we don't have this diagram in front of us, yet we still want to evaluate the sine of 5 pi over 6. Well, you do have to realize that this is in the second quadrant. This is our second quadrant over here. And so 5 pi over 6, you see the over 6 here. That's going to correspond to the pi over 6 in our first quadrant. So you see we can form an angle, a triangle like this. You see this angle here, 5 pi over 6, that angle is going to be similar to this angle in some sense. So you have to also remember that the sine in the first quadrant is positive, and in the second quadrant the sine is also positive because it's the y coordinate. So 5 pi over 6 is going to be the exact same value. The sine of 5 pi over 6 is going to be the exact same value as the sine of pi over 6 in the first quadrant. So this is just going to be the sine of pi over 6, which is going to be 1/2. Now the cosine of 5 pi over 6, well, the 5 pi over 6 is in the second quadrant again, and this is going to be similar to the angle pi over 6 in the first quadrant. However, now you have to remember that the cosine is positive in the first quadrant, but it's actually negative in the second quadrant, because the x values here, notice how they are negative. So the cosine of 5 pi over 6 is going to be actually negative of the cosine of just pi over 6. And so we're going to get negative root 3 over 2. And then the tangent of 5 pi over 6, well, if you remember this number right here, now the tangent is going to be sine over cosine, so the tangent is positive in the first quadrant, but since it's sine over cosine, it's going to be negative in the second quadrant, and the 5 pi over 6 corresponds to pi over 6 in the first quadrant, and so this is just going to be negative the tangent of pi over 6, and the tangent of pi over 6 is 1/2 over root 3 over 2. And we get negative 1 over root 3. So if you don't have this unit circle diagram in front of you, this technique illustrates how you can just remember the values for these common angles in the first quadrant and then deduce what the trig values are in the other quadrants by realizing whether they're positive or negative and what the angles correspond to in the first quadrant. Now let's take a look at this example. For this problem, we want to find all the solutions theta that are between 0 and 2 pi that satisfy the sine of theta equals 1/2. And then we want to find all the possible solutions to sine theta equaling 1/2. So to start this problem, what we can do is go back to our unit circle diagram. So let's take a look back at that. So here we have our unit circle diagram, and on this diagram, remember that we have the terminal side of various angles, like pi over 6, and the corresponding points on the unit circle. For example, root 3 over 2, comma 1/2 is the point on the unit circle that corresponds to the terminal side of the angle pi over 6, as we have labeled right here. Now recall the definition for the sine function with respect to the unit circle diagram. The sine of theta is defined to be the y-coordinate of these points as we move around the unit circle. Remember that if we form a triangle, like right here, if I consider the angle pi over 6, we have this triangle that we can form right here. This distance y is the y-coordinate of this point. This distance x is the x-coordinate of that point. And since this is a unit circle, the length of your hypotenuse is 1. So remember that the sine of theta is opposite over hypotenuse. So you see, in this case, we have that the sine of theta is y divided by 1, or just y. All right, so we want to find all the solutions to sine theta equaling 1/2 for this problem. So if we look around the unit circle for all the points that have a y-coordinate of 1/2, we see that pi over 6 is one solution. So this angle right here is pi over 6, and that's going to be a solution to this equation. If we look over here, we see another positive 1/2 in the y-coordinate. So this angle right here, 5 pi over 6, or 150 degrees, will also be a solution. And then looking around the rest of the points, there are no other points that have a y-coordinate of positive 1/2. So our only two solutions that are between 0 and 2 pi, remember the angle 0 is this angle right here on the positive x-axis, and then 2 pi means we go all the way around 360 degrees, or 2 pi radians. So the only two angles that satisfy this equation are pi over 6, which also corresponds to 30 degrees, and 5 pi over 6, which corresponds to 150 degrees. So these are our solutions to part A of the problem. Now to find all the possible solutions to this equation right here, just take note that if we move through an angle pi over 6, that's the same as if that gives us the same terminal side if we were to move all the way around another 2 pi radians, or 360 degrees. So in other words, the angle pi over 6 and the angle pi over 6 plus 2 pi have the same terminal side. And so the sine of those two angles are going to be the same. That's another way of saying that the sine function is periodic of period 2 pi. It repeats every 2 pi units. So we see that the solutions to this problem in general are going to be pi over 6 plus all multiples of 2 pi. So pi over 6 plus 2n pi, where n is any integer. Just take note that if we go around 2 pi units and then we were to go around again, that would be 4 pi, or 2 times 2 pi. If we were to go around again, that would be 6 pi, or 2 times 3, 2 pi times 3, and so on. And we can also go backwards. Okay, pi over 6 minus 2 pi, pi over 6 minus 4 pi, and so on. And we can do the same thing with 5 pi over 6. So these are all of our solutions. And this would be for n being any integer. 0, 1, 2, 3, negative 1, negative 2, negative 3, and so on. So this is our solution to part B of the problem. And let's take a look at this graphic to illustrate the solutions to this equation. Now let's consider this graphic right here. This curve is the sine function, y equals sine theta. And the straight dashed line is the curve y equals 1/2, the constant function. So we have those two graphed. And we see that the sine of theta equals 1/2, where the two graphs intersect. So we see right here, and you see that's at pi over 6, when theta is pi over 6. Right here, and that's when theta is 5 pi over 6. And then all the way over here, if we move over, you see this point right here is pi over 6 plus 2 pi. 2 pi being 12 pi over 6, so pi over 6 plus 12 pi over 6 is 13 pi over 6. And then over here is 5 pi over 6 plus 2 pi. So 17 pi over 6 is 5 pi over 6 plus 2 pi. And then we can't see it, but off to the right, if we were to look at theta, when theta is pi over 6 plus 4 pi, that would also be an intersection point over here to the right. And if we were to look at 5 pi over 6 plus 4 pi, that would be another intersection point. And also going backwards, we have other intersection points back here, like pi over 6 minus 2 pi, pi over 6 minus 4 pi, and so on. And so this graphically illustrates the solutions to sine theta equaling 1/2. All the solutions to this between 0 and 2 pi, which is right here, are these two. And then in general, all the possible solutions are pi over 6 plus 2n pi and 5 pi over 6 plus 2n pi, where n is any integer.